computers were originally designed to process and store data. But as more computers emerged, a new challenge arose. How could they communicate and share information? This need gave birth to networking. To communicate, computers required a unique identifier, a numeric address known as an IP address, Internet Protocol Address. Just like phone numbers help us connect with individuals, IP addresses allow computers to recognize and exchange data with each other over a network. But as the number of computers exploded, a massive interconnected system emerged, what we now call the Internet. The Internet is essentially a global network of billions of connected computers and servers that share information. Each website you visit, like www.google.com or www.facebook.com, is actually a computer or a network of computers with a unique IP address such as 142.250.182.14. However, memorizing these numerical addresses quickly became impractical. Imagine having to remember different IP addresses for every website. This is where the domain name system, DNS, came in. DNS acts like the Internet's phone book, allowing users to type a domain name like google.com instead of its IP address. It translates human-friendly domain names into machine-readable IP addresses, ensuring seamless browsing. Without networking, the Internet as we know it wouldn't exist, and without DNS, navigating the web would be a nightmare. So next time you enter a web address, remember, behind that simple name is a complex system working to connect you to the right computer in milliseconds. This video will explain everything about DNS, how it works, its components, types, and common DNS attacks. How DNS works. DNS resolutions process. The process by which domain name are converted into IP address are called DNS resolution. DNS resolution follows a step-by-step process where multiple servers work together to retrieve the correct IP address. Here's how it happens. 1. User request a domain name. When you enter a domain name, for example, www.example.com, in your browser, your computer first checks its local cache to see if it already knows the corresponding IP address. If not, it sends a DNS query to a DNS resolver, usually provided by your ISP. 2. DNS recursive resolver. The recursive resolver, also the DNS resolver, is the server that receives the initial DNS query from a client, for example, your computer or smartphone. Its primary job is to find the IP address associated with the requested domain name by querying other DNS servers in a hierarchical manner. It acts as an intermediary between the client and the DNS infrastructure, handling the entire resolution process on behalf of the client. The resolver first checks its local cache to see if it already has the IP address for the requested domain. If the information is cached and still valid, based on the TTL value, it returns the IP address immediately. Initiates resolution. If the information is not cached, the resolver begins the resolution process by querying the root name servers. 3. Root name servers. The root name servers are the first step in the DNS resolution process after the recursive resolver. They are the top-level servers in the DNS hierarchy and do not store IP addresses for specific domains. Instead, they direct queries to the appropriate top-level domain, TLD servers, based on the domain extension, for example, .com, .org, .net. 4. Top-level domain, TLD, name servers. TLD name servers are responsible for managing domains within a specific top-level domain, for example, .com, .org, .net, UK, and .us. They do not store the IP addresses for individual domains, but know the authoritative name servers for each domain within their TLD. For instance, the .com TLD server knows the authoritative name servers, for example, .com, but does not know the IP address for www.example.com. After receiving a referral from the root server, the recursive resolver queries the appropriate TLD server. For example, the .com TLD server for www.example.com. The TLD server responds with a referral to the authoritative name servers for the specific domain. example.com. 5. Authoritative name servers. Authoritative name servers are the final authority for a domain. They store the actual DNS records, for example, AAAAA CNAME, MX, for the domain and provide the IP address or other information requested in the DNS query. These servers are typically managed by the domain owner or their hosting provider. Authoritative name servers receives query from TLD server. It finds the IP address of www.example.com and then returns the IP address to the recursive resolver. The resolver caches the response and sends the IP back to the user's browser. Security and attacks against DNS servers. Because DNS is a widely used and essential service, it is also a prime target for cyber attacks. Securing DNS is crucial to preventing data breaches, malware distribution, and unauthorized redirections. Common DNS attacks: DNS spoofing, cache poisoning. DNS spoofing, or cache poisoning, is an attack where a hacker injects fraudulent DNS data into a DNS resolver's cache, leading users to malicious websites instead of legitimate ones. DNS hijacking. The attack injects a false IP address for www.bank.com into the resolver's cache. The resolver caches this incorrect IP. Prevention: DNSSEC, Domain Name System Security Extensions, short TTL, time to live for DNS records, randomized source ports and query IDs. DNS hijacking occurs when an attacker takes control of a DNS resolver or modifies DNS settings to redirect traffic to malicious sites. In DNS hijacking, attackers compromise a user's router or DNS settings. The DNS queries are redirected to an attacker-controlled server. The attacker sends false responses, directing users to phishing or malware sites. Prevention: use secure and trusted DNS resolvers, for example, Google. DNS 8.8.8.8, Cloudflare 1.1.1.1. Disable automatic DNS configuration on routers. Regularly scan for DNS configuration changes. DNS tunneling. DNS tunneling is an attack where data is covertly transferred through DNS queries and responses, bypassing security measures. In DNS tunneling, attackers encode malware communication inside DNS queries. The organization's firewall does not block DNS requests, allowing hidden data exfiltration. Attackers use DNS requests to control infected machines remotely. Prevention: monitor DNS traffic for unusual query patterns. Use DNS filtering and allow only legitimate queries. Block non-essential outbound DNS traffic. DDoS attacks on DNS, DNS amplification. A DNS distributed denial of service DDoS attack overwhelms a DNS server with excessive queries, causing disruptions. In DDoS attacks on DNS, attackers send small DNS queries with spoofed IP addresses. The DNS server sends large responses to the victim's system. The victim is overwhelmed with traffic, causing a service outage. Prevention: use rate limiting to control query traffic. Deploy Anycast DNS to distribute queries across multiple servers. Implement DNS response rate limiting (RRL). Subdomain takeover. Subdomain takeover happens when attackers gain control of an unclaimed or abandoned subdomain and use it for malicious purposes. In subdomain takeover, a company forgets to remove DNS records pointing to an external service, for example, GitHub pages, Heroku. Attackers claim the abandoned service and host their own malicious content. Users visiting the subdomain are redirected to phishing sites. Prevention: regularly audit DNS records and remove unused ones. Use wildcard. CNAME records carefully. Monitor DNS activity for anomalies. Don't forget to like, share, and subscribe for more tech and cybersecurity insights. See you in the next video.